So here we are. This is the last lesson that I would like to share with you, and that's the fundamental theorem of calculus, part one. I can't really feel good about giving you something called a calculus class without talking about fundamental theorem of calculus. So we've spent several days looking at antiderivatives. The last topic I would like to show you is the fundamental theorem of calculus. We use antiderivatives to calculate the area under the curve. So let me show you how this works. This is why we have to know those antiderivatives. From your middle school and your elementary school days, you have the formulas to calculate the area of different geometric figures. And so this is just a figure that I grabbed off the internet. We know the area of a square, we know the area of a rectangle, and a parallelogram, and a trapezoid, and a rhombus, and two types of triangles, and a circle. And you can break all those apart and put them together and have composite figures and calculate all of those areas. But what about a more complex figure? So what about an area that looks like this one, that gray area? It's the area under a curve, but between two endpoints, two end values, A and B. This shape is not one that would fit on that formula section from above. It's this funky shape, so we need another way to find the area. And what we do, what calculus does, is it breaks that area into smaller rectangles to estimate the area under the curve. So the next picture is a slightly different curve, but if you take all those blue rectangles, they estimate the area under the curve. You find the area of each rectangle, you add them all up, and these are called Riemann sums. Now, we would normally have a lesson about Riemann sums, but we're just going to skip over those for now. And you can use trapezoids to get an even more accurate picture. There are different ways to break up those rectangles into Riemann sums. Oops, I've got flies outside. We can have left or right hand endpoints, or midpoints is what they're called. So with this figure that's in these light blue colors, the lightest blue is a left Riemann sum, and the right blue is the dark blue is a right hand Riemann sum. But I don't care about left and right so much for these, but what I want to show you is that the more rectangles you get, the more accurate that area underneath the curve starts to be. So in this first one, I've got two rectangles. It's an okay estimate, but it's not that great. Then when we get to 4 rectangles, okay, this is getting a little bit better. And then when we got here to 8, yeah, it's really starting to estimate the area under the curve. Well, if I took those 8 and turned them into 16, that would be better. 32 would be even better. 64 would be even better. But then what would be the best? What's one of those big ideas that we've talked about this year? That's infinity. So to get the best calculation of area, you need to imagine an infinite number of rectangles under the curve between those two endpoints. This is called definite integration. So this picture on the right would be all of those rectangles added up. That's your summation. And then if you had an infinite number of rectangles, this is what it looks like with integration. So the fundamental theorem of calculus gets that integration piece for us. So from the area under the curve to the definite integral, we were talking about indefinite integrals, this one's a definite integral between A and B. What does this really look like? We will now work backwards, taking a function f of x and finding what capital F of x function gives us that derivative. This process of finding an antiderivative is called antidifferentiation or integration. That's exactly as it was in the last lesson. So 4 examples, I want you to see what this looks like. Evaluate the following function using the fundamental theorem of calculus. So I've already sketched this picture for you. You don't have to have the picture, but it's a nice visualization to see what's going on. This is x cubed plus 1. I used Desmos to graph that, and took a screenshot. And we are going to integrate between -1 and 3. So again, that means the area under the curve. So I want to sketch that in for you, shade that in. So -1 is here, and 3 goes to here. My highlighter's a little bit too thick, but it's all of this area under the curve. That's what we're going to use calculus to find, is that area under the curve. So the fundamental theorem of calculus will do that for us. So we have x cubed plus 1. So from the last lesson on antiderivatives, the antiderivative of x cubed is going to be x to the 4th over 4 The antiderivative of 1 is x. We talked about plus c. So today I have these boundaries. I have this -1 and this 3. The lower one is the a, and the upper one is the b. We're going to carry those down here, -1 to 3. So what we need to do is put those boundaries into this new antiderivative. So this is 3 to the 4th over 4 plus 3 plus c. And then you do it all again with a -1. -1 to the 4th over 4 plus a -1 plus c. And we're going to subtract these. So we have to go through and figure out what this is. So 3 to the 4th is really 81/4 plus 3 plus c. Now I'm going to distribute this negative sign to each one of these. -1 to the 4th is a +1 over 4, but I'm going to distribute that negative, so it's a -1/4. -1 with a distributed negative becomes +1, and positive c becomes a -c. So when you're looking at this problem, what you have to ask yourself is what happens with c? I have a positive c and a negative c. Those cancel out. And then we add the other pieces together. 81/4 minus 1/4 is 80/4. 3 plus 1 is 4. 80 over 4 is going to be 20. Plus 4 gives us 24. So the area underneath that curve between -1 and 3 is 24 square units. We don't bother writing square units. I know in elementary school you had to worry about inches squared, feet squared, maybe even in your science class or physics class, but we just need 24. Know that that integral is calculating the area under the curve. I want to come back here and talk about c real quick. Here's a positive c and here's a negative c. That's going to happen every single time. You'll always have a positive c and a negative c. So we actually don't bother writing it back here in this step, but I just wanted to illustrate for you that it will cancel out. So when I do example 2, I won't write it out that time. So let's try another one. Evaluate the following function using the fundamental theorem of calculus. So I've got the square root of x. Square root of x I've sketched over here. We are going to graph between 0 and 1. Let me grab my highlighter. So between 0 and 1, that's this area in here. Again, imagine an infinite number of rectangles making all of those up. We're kind of skipping over that step, but that's what's really happening. You have an infinite number of rectangles. So this is equivalent to the integral from 0 to 1. How do we rewrite square root? With a 1/2 exponent dx. What's my new exponent? It's 3/2. Divide by 3/2. I would put a plus c, but I don't have to worry about it. Between 0 and 1. So instead of dividing by a fraction, we multiply by the reciprocal. This is 2/3. X to the 3/2 between 0 and 1. Now we put in the 0 and 1. So 2/3, 1 to the 3/2, minus 2/3, 0 to the 3/2. So this first piece becomes 2/3. The end, that 0 is nice. Anything times 0 is 0. So my answer is 2/3. I kind of like this problem. If you look at this box, it's 1 unit wide and 1 unit tall, so its area would be 1 square unit. I am saying that the shaded region is 2/3, so I'm saying that it's a little bit more than half, which sure, if I connect it along the diagonal, that'd be half. This is a little bit more than 1/2. So there we go, an area of 2/3. Example 3, evaluate the following function using the fundamental theorem of calculus. Between -2 and 1, e to the x. So I've already sketched e to the x for you. I get bored with colors, so I gotta use all of them. So we're going between -2 and +1. You're calculating the area under the curve. That's what that fundamental theorem of calculus does for us. So this one's easy. The antiderivative of e to the x is e to the x between -2 and 1. So this becomes e to the 1 minus e to the negative 2. Now, I don't have a calculator with me, but you could figure out what that is as a decimal. You could also see this written as e minus 1 over e squared. Now, if I'm getting really fancy here with common denominators, this could be e cubed over e squared minus 1 over e squared, which would be e cubed minus 1 over e squared. Again, you could turn that into a decimal and tell me what that exact area was. So, fundamental theorem of calculus, last one. Evaluate the following function using the fundamental theorem of calculus. I have the graph of 1 over x. We are going to integrate, find that area between 1 and x. So, oh, sorry, not 1 and x, 2 and 8. So here's 2. I think I need to zoom in here. This one's so teeny tiny. So here's 2, and all the way down here to 8. Yes, my highlighter goes outside of that area, but just keep in mind that's that little sliver that we're trying to find the area for. So when we go to calculate this, the antiderivative of 1 over x, we talked about this in the last notes, is the natural log of the absolute value of x between 2 and 8. So this becomes the natural log of 8 minus the natural log of 2. This is going to be a crazy decimal. That's okay. Remember, with subtraction, that really becomes division. So this is natural log of 8 over 2. If you didn't remember that, that's okay too. 8 divided by 2 is 4. This is the natural log of 4. So great job. Fundamental theorem of calculus, part 1. I'm going to give you a few examples to try today, a few examples on Delta Math tomorrow, and you guys are finished. I really, really, really appreciate you working from home. I know that this is tough, but I really do appreciate your efforts. And when you send me notes, hey, your video is missing, it makes me realize that you are looking for those videos. So that actually means a lot to me. So thank you so much, guys. And yeah, let me know if you get stuck. I'll help you out.